I am recording.
Nice. So yeah, let's talk about the system overview chapter of PBRT, which this code base is pretty well structured and also like I just get it built on the first try. So it's pretty neat.
That uh, Visual Studio you used to build it.
I use CLime, but yeah, MSVC.
Okay.
Yeah.
My experience with building on Windows is relatively limited. Been trying to do more of that. So it's progress. It's a process. Yeah.
What you said?
Oh, just yeah, the setting up to build on Windows is a little bit of a process.
I feel like it's all right.
Yeah, it's a little bit of a change from what I'm used to as well.
Those are just introductory text. Uh, and phase of execution, PBRT can be divided into three phases of execution. First, we parse the scene description file. And then we have a basic scene class, which stores the scene specification, but not yet suited for rendering. I also have a lot of those kind of stuff in my project, which I really don't know how to name those things. Not that basic thing is a very good name, but just it's hard. I sometimes name it CPU scene and GPU scene because I gather the specification on CPU and then upload to the GPU. But obviously PBRT is not the case, so maybe basic scene will work. In the second phase, PBRT creates objects for the scene, for example, camera. But yeah, previous PBRT intermix those two phases, but yeah, this version because we have GPU, so we need a uniform representation for the scene, and then we need specific representation at runtime. And the third phase, just render loop. And the main function first parse CLI. And mainly it's just parse CLI, parse the scene, and then render, which calls either render wavefront or render CPU. Notice this is a long chapter, so yeah, no way I will read all of those. For you, I would
Yeah,
just read
skimming it's just
parts I
fun.
think is important. Yeah. So I still expect you to take your own time to read this. And yeah, and the integrator is the important part of the PBRT. But this integrator only works on the CPU, and they have a separate wavefront integrator, which have different interface. And this one only works for the traditional CPU rendering, so they still use virtual functions, which is fine. Interpreters takes a primitive which is just like the root of the thing, I guess, and then also a vector of lights. Yeah. And I guess for the lights, something needs to be done to pre-process the light because some of lights need to know the bounding box of the scene, which obviously when lights get constructed, they don't know, so we need to do that. And then there are some infinite lights, we need to put it into a separate vector. So that's this part. And the integrator provides a render method which will be implemented by subclasses. And this method is called by the render GPU functions. Sorry, render CPU function. Oh, right. They are also implement some STD stuff because they basically want to add that CUDA annotation to it. So yeah, it's nice to use optional rather than alt parameters. Uh, Also everything in PBRT using uppercase float, which they can be toggled as double. And there is also an intersect P, which is like this intersect. But yeah, also returns a Boolean indicator. This is for shadow ray stuff, I guess. Now this is image tail integrator, which deal with image tail. And it's interesting that not all integrator in the PBRT are image tile integrator, and that's why they make it separate. Yeah, so all the I guess it's most integrators render images use a camera model to define the viewing parameters and then rendering by splitting the image into tiles and having different processors working on different tiles. So yeah, they deal with that. Basically, you have a camera and a sampler to dispatch, and also some functionalities to dispatch work to different threads. And yeah, for all PBRT integrators, the final color at each pixel is based on random sampling algorithms. So that's why the sampler is also a polymorphic type. Also, yeah, for the image tile render, we first just create a bunch of variables and then render image in waves. So they have they have those thread local scratch buffers for just those are basically arena allocation or bump allocator, if you want to call it, which are very cheap to allocate. And yeah, so I don't know what that's why they use this thread local, but apparently, probably they find the language thread local insufficient, so they use this custom type. They also have different samplers for each thread because, yeah, you definitely don't want risk condition when using samplers. And so also some other stuff like sample per pixel, the pixel bounds, and also like a reporter for the progress. And then finally the render loop, which rendered image tiles in parallel. And they use this parallel for 2D utility that takes a pixel bound and then a lambda. And this is what inside the lambda where the loop through the tile bound for the 2D point and then render samples for each individual pixel. And then after the image tile integrator, which basically deal with just infrastructure stuff, we have this ray integrator, which actually do some like ray tracing algorithm stuff. And yeah, it's a subclass of the image tile integrator. It implements a pure virtual evaluate pixel sample method from the previous image tile integrator, which at each given pixel it uses a camera and a sampler to generate a ray into the scene and then call the LI method, which is denoted for the symbol Li in the rendering equation that calculates the radiance at that particular sample. Here is the image on what happened. Basically, we have this evaluate pixel sample function which get called for each individual pixels, and then it first get a sample from the sampler, use the sample to get a ray from the camera, and use the ray and to get an instance radiance from that Li function, and then finally get the result, write the result into the film. Yeah, which is basically what's talked about in here. They get a sample and then use that to get a sampled wavelengths from the camera. So PBRT doesn't use RGB anymore. It's all wavelengths. That's neat.
That's pretty phenomenal in a way that it's like we got to the point where we can use wavelength or you know this type of rendering as the default.
Yeah. And GPU. Its GPU rendering is also decently fast.
Yeah.
Definitely not something that you would describe as high performance, but it's offline render, so it's not even be that highly optimized, mainly for educational purpose, and it's already decently fast, so really neat. Yeah. And also we need to get a actual camera sample and then generate a ray from that sample. camera interface provide two functions for generate ray, which generate ray and generate ray differential. So ray differential, which will be actually used in here, my understanding it's for texture kind of stuff. But I never implemented ray differential in any of my ray tracers, so I don't know actually. But let's say later. So it uses ray differential. Basically, just think about ray differential as ray with some extra information. So we get a ray, and then we need to do some processing for the ray differentials. We evaluate radiance along the camera array, which is the main part. And finally, there's some just defensive programming. And yeah, the main part is to calculate the actual radiance by calling that Li function, which is also a pure virtual function again that it's subclasses of ray integrator implement. And then it's multiplied by this weight function. So the weight value of this ray. And also, yeah, a common bugs of the render process is some impossible radiance values. For example, nan or infinity. So it's good to track them and report them. And this random walk integrator implements reintegrator, and I think it's just a very brute force path tracer. It doesn't use anything fancy. But yeah, it can generate this pretty good looking result. It can't handle mirror reflection though, so
Bit surprising that it can't, but because I see the highlight off of the lampshade has, reflecting something about it, but I wonder if the coffee is just very dark.
but the perfect mirror reflection, it definitely can't handle that.
Ah,
Yeah, but for those kind of imperfect metal-like things, I don't see any problem. Just brute force path tracer, yeah. Which when remember in the ray tracing when we can't, they need some very specific things for mirror. Basically, you can't use BRDF for that.
oh,
So yeah, random walk integrator, which its li just calls li random walk because it's a recursive function. Which, to be honest, I'd rather write it in a loop, but whatever. And our random loop first intersects ray with a scene, and then if no intersection, we just returns. And then we get the immediate radiance by recursive. No? Oh, it's emission. Yeah, we get emission. And yeah. Terminate random walk if maximum depth has been reached. We get the BSDF at this point. And get a leaving direction by using the sampler. And then validate BSDF at surface for the sample direction. This is the main part. And then we do the recursion by recursively call the li random walk with a new spawned ray. And yeah, here is our rendering equation, which corresponding to this part. To divide it by 4 pi here. And we get this, we get this image, which looks already pretty nice. If we can do some denoising afterward, but with similar amount of work, with some important sampling, we can get significant better result. We assume this is what pass integrator different from this brute force integrator. Yeah, that's about this chapter.
Cool. Seems like a pretty good overview of the flow of things as the rendering happens.
Yeah. We stop recording.
I will.